So real quick before we do this practice question, I just want to say that this exact question is taken from my Civil FE review course. So if you're looking for practice questions similar to this, where I walk you through the step-by-step solution and also discuss the concept at the same time and reference the FE handbook, make sure you check out my FE Civil Review course. So the link is in the description, and if you have questions at all about the course or the FE in general, please reach out to me directly. So now we got ourselves another wastewater treatment example, but here before we do this, don't forget to pause the video and see if you can get what I get. So make sure you struggle with it, attempt this on your own, and be very careful with the units and reading the problem statement slowly and extracting the right variables. So it can be very tricky for this one especially. So here we're told that the primary effluent is to be treated by two parallel trains of the complete mix activated sludge process for a total design flow rate of 2 mgd. So that 2 mgd is just million gallon per day. That's actually the units we use for flow when we're looking at water treatment, or especially in this case wastewater treatment. We usually use the flow rate of mgd, million gallon per day. So the suspended solids and the BOD5 concentrations, the suspended solids and the BOD5 concentrations in the primary effluent flow are 104 milligram per liter and 138 milligram per liter. So it's the suspended solids is 104 and the BOD5 is 138. So be careful, and then it says respectively. So when you read sentences like that, the suspended solids is what comes first, it's 104. Then the BOD5 concentration is what comes second, it's 138. So the sludge is wasted from the secondary clarifier, and the effluent suspended solids concentration is negligible. So we can neglect that. So here we're told to assume the following parameters. So assume the following for the activated sludge process. So the plant effluent BOD5 is 8 milligram per liter. The biomass yield is 0.55 kilogram of biomass per kilogram of BOD. The endogenous decay rate, K sub D, this K sub D value is 0.04 per day. So day raised to the -1 is just 0.04 per day. Then the solids retention time, it's for the solids in this case, which is going to be theta sub C, is 8 days. And the MLBSS, or you can say, usually they give you the MLBSS or the MLSS concentration in the aeration tank is 3000 milligram per liter. So we're given all these properties as well. So the goal is to do what? The required volume in cubic meters of each aeration tank is most nearly what? So that's what we want to find, right? Find, we'll say the volume. I'll do this symbol for volume, or you can use V for volume. So V, we usually use it for velocity, but that's what we want to find, the volume. And we want units of cubic meters, right? That's the goal. So that's what we want to find of the aeration tank. So if you look at this, and if this is your first time, this can be hard to just even solve if you haven't seen this in a while, right? Or it's just, you have to have a visual representation of this stuff. And this is the purpose of this practice question and your overall FE review, right? So here, what I want to do first is the following. So I want to just look at this treatment process and focus on the primary treatment and secondary treatment, okay? So now, we know primary treatment consists of just basically removing the solids, right? That's primary treatment. And we know it's a slow process, and it utilizes filtration and sedimentation, and also we remove like the cans of Coke or bottles through screens as well. So you have the screening, grit chamber, and you also have the primary clarifier or the primary sedimentation basin here that can also, same thing, think of it as the same thing in this process, which is primary treatment. So what I'm going to do is say this. This is my primary. We call that the primary treatment. I'll just call it primary. Then what comes after primary is secondary treatment. Secondary treatment, which is your biological treatment. So it uses the biological processes for extraction and we use the we break down the BOD, we actually remove BOD through the microorganisms, right? So they do that job of breaking down BOD, and we know it uses both anaerobic without oxygen, and aerobic breakdown processes as well. So you may have microorganisms that don't need oxygen, which is anaerobic, no oxygen, and you also have microorganisms that do need oxygen to break down that BOD or break down the waste in this aeration basin, and that's why we would add some air to give them that oxygen, right? To give the microorganisms the oxygen. So now we know after primary is going to be secondary treatment. And what I'm going to do is denote that right after, so let me write it like that. This is the secondary. And I want to note here that disinfection is part of the secondary, but usually what we focus on as the most important process in the secondary is the aeration and the secondary clarifier, and that's called the biological treatment or the activated sludge treatment. So this portion, let me denote it here. This portion is the activated sludge. So the one we're going to actually focus on is going to be this portion, the activated sludge treatment. We have the aeration tank and we have the secondary clarifier. Note the primary clarifier is like your first clarifier, and that's part of primary, right? And it has some sludge that comes out, right? Some waste that comes out, which we usually like dry out and apply it for land application. But the secondary clarifier is part of this, right? The aeration tank and the secondary clarifier is your overall biological treatment or activated sludge treatment, and that's the one we will focus on for this example. So let's go back above. Let's not forget what we want to find. It's the volume of the aeration tank, right? So where's that aeration tank? It's part of this secondary treatment, essentially, where we have that biological treatment, activated sludge. So that's what we want to find. We want to find the volume of this tank. Volume of the tank. And we're given a lot of things in this problem statement, and I want to point out a few things using the handbook, okay? So I want to point out your recycled flow rate, your QR, your QW, I'm looking in my handbook, QE, and all that stuff, using this diagram. So let's do that together. Maybe you can attempt to do this, pause the video on your own, and label these variables, because they give us no picture, right? You have to know exactly where these lie. If you have to visualize this thing and know the variables, so it can be difficult. So here we'll go step by step. So it says under steady state mass balance around the secondary clarifier, let's label our Q naught plus QR. Q naught plus QR. So note that Q naught is your influent flow rate. It's the influent flow rate that comes from primary treatment, right? That Q naught. So I know the influent flow rate is going to be here, right? It's essentially this. It's Q naught, and it comes from after primary treatment. Q naught. This is actually your total design flow rate, right? It's the total design flow rate. So then it says Q naught plus QR when you're looking at the steady state mass balance around this stuff is going to be the Q naught, which is this after the primary, right? And then you add that QR. It's what gets recycled, right? The flow rate recycled, which is going to be my QR here. So Q naught plus QR is actually what comes in the aeration basin. So it's going to be this portion. This is my Q naught plus QR. Q naught plus QR. So I hope that makes sense. It's QR plus Q naught. You're basically doing like a mass balance or a nodal equilibrium analysis around that node, and you get Q naught plus QR, right? It makes sense. And that's what comes out here and goes into the aeration tank. Q naught plus QR. And that's what they're talking about. That's what they're talking about there. So now if we look at the next variable, XA, so that XA, it says it's the biomass concentration in the aeration tank. They denote it as MLSS or MLBSS. So it's actually the MLSS, right, in the tank, and I'll just label it XA. And it's like the suspended solids. Anytime you see suspendeds or biomass concentrations, it's always your axis. So here it's the XA in the tank, which is going to be this one, right, XA. And here I notice that this Q naught plus QR is multiplied by XA. It makes sense as to why, right? This Q naught plus QR comes in the tank, then it's the same Q naught plus QR, the total Q naught plus QR flow that comes out of the tank, right? So I can actually denote it here as well, Q naught plus QR. So this Q naught plus QR comes in the tank, then it comes out of the tank with this biomass or suspended solids concentration, MLSS, and times your Q naught plus QR, right? That comes out of the aeration tank. So we took care of that. Now QE. QE is what comes out of the secondary clarifier. So let me denote it here. QE, the flow out. Then we have XE, which is going to be the suspended solids concentrations that comes out of the secondary clarifier. So we took care of that. Then what else do we have? We have QR, then XR. So QR, we labeled this. It's what gets returned, right? It's the recycled or what gets returned. So that's going to be QR, and we will have a suspended solids concentration, XR. Then we are almost done. You have Q waste and X waste, and that's going to be what gets wasted. So that has a QW, XW. QW, XW, then we like dry the what gets wasted. We have that sludge. Then we dry that thing and use it for land application, right? And that's going to be the waste. So those are all labeled, and that can be very tricky, right? That can be tricky. And the volume, the V value, is just V. It's just your volume of the tank. Volume of the tank. And that tank will also have the hydraulic residence time. So it's your residence time there. And you will also have something called the theta sub C, which is your solids residence time. So this is the hydraulic residence time, just looking at the water. The solids residence time considers the solid portion that comes into the tank per day, right? You take the flow times the time and you get that solids portion. So the theta sub C is for the solids. Theta is going to be for the hydraulic residence time, and we're going to actually use that. So this is important, and you have to know this. You have to know this. So try to redo this on your own, pause that video, and relabel this thing with the variables in the handbook. We're using the FE handbook. So now let's go back above. We needed the conceptual understanding of these variables to actually solve this question and maybe solve other questions similar to this. So we have this. We want to find the volume in the aeration tank. And now for the solution, what I'm going to actually do is as follows. What I'm going to do is create my own figure, create the own figure. And what I'm going to say is, let's say we're focused strictly on the activated sludge process. Let me draw an aeration tank here, and let me draw the clarifier here. So the secondary clarifier. And I'm going to draw another one. You'll see why. Same thing, aeration tank. And you have a clarifier as well, secondary. So why did I do this? Why did I draw two? Because of this keyword, two parallel trains for this activated sludge process. They're two trains, so you have to be careful with this. But the total design flow rate that's actually coming in is 2 mgd, right? So what happens here? What happens is you have the 2 mgd that comes in, 2 million gallon per day, and it comes in from where? It comes in after primary, right? After the primary treatment. That's what comes in. Then we know that is going to get split, right? It gets split into two because we have a parallel train. So here you have 1 mgd that comes into the secondary treatment or the activated sludge biological treatment, and you have 1 mgd there. So that can be tricky. You cannot just use 2 when you're using that Q value when you solve this. So you have parallel. Anytime it says parallel, make sure to split the total flow, right? The total flow, which is essentially we denote as Q naught. Q naught is the total flow that comes in, right, after primary. So we have that, and then after that, the way I drew this then is this comes out. It's the same thing as we've labeled. This is your XA, this is your MLSS. Then it comes out the aeration. This is the aeration. You have XA, and then you have MLSS. And note, this is the aeration, right? The aeration basin or the aeration tank, same thing. And then after the aeration you have the secondary clarifiers. So with that you have the effluent, I'll call it EFF for effluent, and that effluent we know is what comes out here. It has a XE or SE as well, and QE for the effluent after the secondary. Then we also have a waste. Then we have waste for this. What gets wasted is going to be QW as XW, QW, XW. Then we know some of it gets wasted, but also some is going to get recycled, right? So QR, XR, just like what we labeled below. So same thing here, QR, XR, recycled, QR, XR for that one. So now, having this, we can proceed now just so we have a visualization. But the most important thing I would say is that splitting that 2 MGD. Make sure you split that. So now what I'm going to do is just use an equation in the handbook, right? You're not going to use the steady state mass balance around the secondary clarifier, which is this, right? These are the secondary clarifiers. What we're going to actually use is the first equation under activated sludge. And I'm going to write that equation down for us. So it's going to be XA equals to theta sub C, the solid's retention time, times your Y value, times S naught minus SE, divided by your theta, and that is going to be 1 plus KD. 1 plus KD times theta C, again, theta C, theta C. So now, how would we do this? We know we want to find the volume, right? And there is one very important definition that relates the volume of the tank, of each tank in this case, keyword, each tank. The volume of each tank can be arrived at by doing what? We know the volume, let me write that here, is going to be related to your Q value and your residence time, right? So the volume is just your Q value times your hydraulic residence time, or the detention time. So what we will do at the end is actually use this equation to find the volume, right? So we know Q we know, right? Q is going to be just 1 MGD for each tank. So we know Q, and theta is going to be the value we will find using this equation. So we're going to find theta and plug it in here, then solve for volume. So you have to know this definition, and it's actually in the handbook under those variables. They give you the definitions of a lot of these variables. It's in the handbook. And it says the hydraulic residence times is V over Q, right? So you just solve for V here. So now, using this equation, let's plug in all our variables and solve for theta. But before we do this, I just want to have an equation for theta, right? You can do it this way, or you can try using the solver. So let me know down below what's your quickest method to solve this. Maybe under 3 minutes, 4 minutes, probably 3 minutes. And see what works best for you. But the way I did this is solve for theta first and rearrange this. So what I'm going to do is focus on solving for theta. So I'm going to multiply this side by theta plus times 1 plus KD times theta C. And I'm just taking this, multiplying by this side. But what I do to this side, I must do to this side. So you multiply theta 1 plus KD theta C. This is a multiplication. So these cancel. Now on the left side, I have this portion. I'll just rewrite it since we're learning this stuff. KD theta C. Then you multiply by XA. And that equals to theta C times Y. And you have S naught minus SE. So now we're basically done, right? You just solve for theta by itself. So what you can do is divide this whole side by 1 plus KD theta C. Then XA cancel, but what you do to that, you must do to this side. 1 plus KD theta C XA. So now you solve for theta, which is your detention time or hydraulic residence time, and you solve for it using this equation, right? So I'll just plug in what we know. So now theta C is given, and that's given in the problem statement to be 8 days, right? 8 days. So you put 8 for that. 8 days for theta C. So now our Y value is also given to be which one? It's going to be the biomass yield, keyword yield, Y for yield, 0.55 kilogram per kilogram of BOD. So 0.55. I'll just write it as kilogram per kilogram, so the units cancel, so we don't really have to worry about that. So that's going to be the Y. So now for S naught and SE, this can be confusing, especially with this problem statement. So S naught is your influent. It's going to be defined in the handbook as the influent BOD or COD concentration. So just note that S is for BOD. So anything with S is not suspended solids, it's BOD concentrations. S is for BOD. So here it says the suspended solids and BOD5 concentrations in the primary effluent are 104 and 138. Which one would you pick for S0? The influent. Not the suspended solids, right? Because the suspended solids is the 104, right? The BOD is what we actually want. The BOD5 concentration in the primary effluent is 138. So that's what we use. We use the 138 for S0. Use 138. So for that one, you use 138 milligram per liter. Then minus our SE. What's going to be the SE? SE is defined as the effluent BOD concentration. And for that, that's actually given in the problem statement, right? Plant effluent BOD is 8, right? That's our SE. It's going to be 8 milligram per liter. It's actually what we want, right? That's like the goal we want to meet of 8 milligram per liter that we get for BOD. So we reduce it essentially from 138 that comes in to the 8 milligram per liter that comes out. So we have that. Then on the bottom, we just put 1 plus KD times theta C. So you take all of that and 1 plus KD is just in the problem statement, and that's going to be 0.04 per day. So 0.04 per day. Then you multiply that by theta C. That's also the same as this, so you just put 8 days. 8 days. Then you take that, close this, and times XA. XA is your MLSS concentration. That's going to be 3,000. So you just put 3,000 milligram per liter. So we're done with this. So if you look at the units, you can actually cancel, right? You cancel these, days cancel. Milligram would actually just cancel this. Well, basically this whole thing is going to be milligram per liter, right? And we know milligrams would just cancel there. This would cancel as well. And you are just left with days. So milligram cancels this milligram, and you should be just left with days. So the units do make sense, and you get an output for your theta of days. Your theta of days. And when you solve for that, you should get a small value of 0.1444 days, right? Days. So be careful with the units on the FE. They might give you seconds or whatever, or the concentrations are different. So just make sure everything cancels there. So we have our theta value. We're basically done. Then we do V equals Q times theta. So the volume for each aeration tank, volume for each, equals your theta value, which is 0.144 days, and you multiply that by your flow. So this is going to be the Q value, right? So what do you use? It's going to be the one that goes for each, because we want to find the volume of each. So that's going to be the Q. That's what we use. So you just take 1 MGD, 1 million gallon per day. So 1 million gallon per day. So 1 million is 1 times 10 to the 6. Then that's going to be gallon per day, right? So now at this point, if we look closely, the days units cancel, and we get units of gallons, right? But we know we want units of cubic meters at the very end. So what I'm going to do is take gallons to liters, convert that to liters, then convert liters to cubic meters. So it goes as follows. So what we will do is take that gallons to liters first. So we know there's 3.785 liters in 1 gallon. This is on the page 2 in your FE handbook under unit conversions. There's a different video for this, for discussing how to do this conversion. So make sure to watch that. But these cancel. Now we have liters. So then we can simply take that value we get for liters and divide by 1,000, because we know 1,000 liters is in 1 cubic meter. 1 cubic meter. So then the liters cancel. The liters cancel. So now we get just cubic meters for the volume of each aeration tank. So when you solve for that, you should get a value of approximately, you get 546,800,000 liters, but that you divide by 1,000 then, which is doing this portion, and you get 547 cubic meters. And that should be our answer. That should be our answer. So I know this was a long one, but make sure you know this stuff. Make sure you know the basic definition of primary and secondary treatment, how to label all of this, and know the variables, right, involved in your calculations. So it's 547 cubic meters. So the answer should be C. That's all for this. Thank you.